So today's lesson is not about mean girls, but it's about the mean value theorem. Okay, one of the most important theorems of early calculus. Okay, you'll see it today in a little bit. Okay, and it's not really that complicated. It's also almost one of those duh theorems. Duh, it makes sense. All right, but the ramifications of this theorem help us prove a lot of stuff in early calculus. And we're going to see some of that stuff today. So the mean value theorem. All right, before we get to mean value theorem, we need to talk about Rolle's theorem. Okay? I can't roll my R's like you would in French. But the Rolle's theorem was developed by Michel Rolle. He was a French mathematician. You might have liked him a little bit because he actually said something about infinitesimal calculus down here at the bottom left. So calculus is a collection of ingenious fallacies. All right, he thought that calculus was a whole bunch of hocus pocus, like y'all do, and there was actually probably some fallacy, some error in it that we were just kind of overlooking. But one of the theorems that helps us prove mean value theorem is Rolle's theorem. This guy, a little bit of background about him. He grew up poor, educated pretty much himself, had an elementary education, but then educated himself and became this great mathematician, worked for the government, in the military. He's probably the reason why we use these symbol for equals. Okay, 2 vertical bars. Somebody else came up with it, but he really popularized it in his notation. All right, that's enough about him, though. Let's get to Rolle's theorem. So what Rolle's theorem says. Okay, suppose that f, a function, is continuous on the closed interval a, b. So it means that all the points between a and b, including a and b, work. All right, it's differentiable on the interval a, b, but this case is an open interval. So the ends, you could have some asymptotes going on. Not really that important. And when you plug in f of a and f of b, they're the same thing. Okay, so I guess you really can't have asymptotes going on because you actually have points there. But at the very ends, f of a and f of b are exactly the same thing. All right, what Rolle's theorem says, if you got those 3 things, which is this is very important for part of your homework, you got to say, hey, can I use Rolle's theorem? Does the function have these 3 things? Okay, it's going to be easy to find. Continuous, differentiable. If it's a polynomial, you can do it. And then just plug in the numbers for f of a equals f of b. But if the hypothesis for Rolle's theorem is true, then we have the conclusion, the then part. All right, and the then part says that there exists a number c, which is an element of a, b. That little symbol means element of, just means, hey, c is somewhere in between a and b, such that the derivative evaluated of c is 0. All right, and it guarantees it. Okay, doesn't actually tell you what it is, but it guarantees that it does exist. So let's see that on a graph. Okay, this is a graphical illustration of Rolle's theorem. Okay, and it's one of those things that makes sense. All right, here I've got a hump. Okay, it's a function from a to b. Notice it's defined at a and it's defined at b. All right, it's also differentiable. There's no corners or cusps or asymptotes in the middle. All right, and notice f of a, the y values at a and b, f of a and f of b, are exactly the same. All right, we got the same thing going on in this graph over here. What Rolle's theorem says, and you can definitely see it, if I'm going to go from a f of a to b f of b, all right, well, if I'm going up at some point, in order to get down to f of b, I've got to do what? Turn around and come back down, and wherever that turnaround point is, that is where the derivative is 0, because the slope of the tangent line at that point is a 0. It's straight across. Okay? It totally makes sense. Okay? Again, I call it a duh theorem because duh. Okay? Proving it is a little bit more difficult, but it does make sense. So the function is either going up, and it's got to come back down, or if it's going down, it's got to do what? Come back up, and at that point, wherever it comes back up, it does have a horizontal tangent line. So the derivative at that c is equal to 0. There's some point between A and B, namely a C point, where the derivative of C, at C, is 0. All right, and guarantees at least one exists. All right, there could be more. Okay, here's an example if there's more. Okay, I got A and B. They have the same exact y values, and this one actually has two places in between A and B where the tangent line is horizontal and the derivative is 0. Okay, there could be tons of up and downs in there. Okay, in fact, you could even have this function, which I'm going to draw in green up here. I could have A f of A here, B f of B here, and I could draw a straight line there. All right, if I draw a straight horizontal line there, well, actually, all the points that this line was truly straight have a derivative at 0. Rolle's theorem just guarantees there exists at least one. Okay, it's an existence theorem. Doesn't actually tell you where it is, but it just tells you that there is one that does exist. All right, so let's do this example. An illustration of Rolle's theorem. Find the value of C satisfying the conditions of the conclusion of Rolle's theorem for f of x equals x cubed minus 3x squared plus 2x plus 2 on the interval 0, 1. All right, so the first thing you want to do when you're trying to apply Rolle's theorem is to test the hypothesis. There's 3 conditions. There we go, 3 conditions. Okay, condition number 1, it has to be continuous between 0 and 1. 2, it has to be differentiable between 0 and 1. And 3, the most important one, if there's one more important than the other, is if you plug a 0 in and you plug a 1 in, you get exactly the same thing. All right, is it continuous? Well, yes, it's a polynomial. All right, any polynomial function is continuous everywhere. Is it differentiable? Again, yes, because it's a polynomial. Polynomial just has smooth curves. It doesn't have any cusp or corners. All right, and finally, does f of A equal f of B? So does f of 0, question mark, equal f of B? All right, so you're going to have to test that out. All right, well, what is f of 0? F of 0 turns out to be 0 cubed minus 3 times 0 squared plus 2 times 0 plus 2. And I know you can do that a whole lot quicker or more quickly because all the first 3 terms cancel out, 0, 0, 0, and 2. All right, so now we just need to confirm that f of 1 is actually also 2. If you plug a 1 in, basically x cubed becomes 1, a minus 3x squared becomes minus 3, a plus 2x becomes plus 2, and then the constant plus 2 is still there. So if I do that out, I get 1 minus 3, which is negative 2 and 2 give me 0, 0 plus 2 is in fact 2. So does the third condition work out? Is f of 0 equal to f of 1? In fact, yes. All right, so I know that I can actually apply Rolle's theorem. All right, so to apply Rolle's theorem, if I want to here, which we're going to, I need to do 2 things. First thing I need to do is find the derivative, which shouldn't be that big of a deal for us. All right, it's just a polynomial, so it's just going to be using a whole bunch of power rules. So the derivative of x cubed is 3x squared. Derivative of minus 3x squared is a minus 6x. And the derivative of 2x is plus 2. All right, it's quadratic, so it'll possibly factor. Well, it doesn't. Okay, so, but if it's a quadratic, we can figure it out because we have something called the quadratic formula. All right, and the reason why we're going to factor it is because Rolle's theorem, the then part says that, hey, this derivative is equal to 0 somewhere between 0 and 1. So I put 0 is equal to 3x squared minus 6x plus 2. Okay, Rolle's theorem guarantees that the derivative is 0 somewhere. It means it has a horizontal tangent. It has a turnaround point somewhere. All right, so this one I believe we're going to have to use the quadratic formula. So it's got x is equal to a negative b, so 6, plus or minus the square root, negative 6 squared, so 36, minus 4 times a times c, so that's going to be 24 all over 2 times a, which is 6. We do a little bit of work. 36 minus 24 is 12. So I get 6 plus or minus square root of 12 all divided by 6. Make sure I did that right. All right, square root of 12 could come out as 4 and 3, so it becomes 6 plus or minus 2 square roots of 3 all over 6, which reduces to 6 plus or minus, oh, not 6. I'm just rewriting the problem there. All right, we realize 2 can go out of 6, 6 and 2, so we get 3 plus or minus the square root of 3 all over 3. All right, so that actually gives us two places where the derivative is 0. All right, but not necessarily both of them are going to be between 0 and 1. Rolle's theorem guarantees that one of them does. So if I look at it, I got negative 3 minus the square root of 3 divided by 3. All right, well, without even sticking that into my calculator, I realize that that is not going to be in between 0 and 1. Because I got a negative minus another number, so that makes it even more negative. And I divide by 3, it's still negative. So if I stick that in my calculator, just to test it out, negative 3 minus the square root of 3, all divided by 3, that actually gives me negative 1.577 approximately. All right, Rolle's theorem didn't tell me that that one exists, it just does exist. All right, but the other ones should lie between 0 and 1. Negative 3 plus the square root of 3, all divided by 3. Stick that in my calculator, negative 3 plus the square root of 3, all divided by 3. I've done something wrong somewhere. Oh, it's not negative to start off with. What? It's what? Equal to. There's a problem. Must have forgotten the equal sign. So let's recalculate that. I was actually kind of probably wrong here. Actually, I think this is the one that's going to work. All right, 3 minus the square root of 3, all divided by 3. That actually gives me a 0.423 if we're rounding. That's the one that he guarantees that exists there. The other one, 3 plus the square root of 3, divided by 3, that actually is equal to 1.577, the positive form of it. And that one's not in between 0 and 1, so that's not the one we're looking for. Okay, these are not the droids you're looking for. Okay, there's our answer. Okay, we found a C between 0 and 1 that has a derivative, when you plug that number in, of 0. And that's Rolle's theorem. Okay, so you got to make sure it works, the hypothesis. So make sure the endpoints do, in fact, when you plug them in, give them the same thing. Then you take the derivative and you solve the derivative for 0. All right, and there is Rolle's theorem. All right, now that example, even though you're going to do some homework problems like that and problems in class, it's just merely an illustration of Rolle's theorem. All right, the power of the theorem is really that it can be used to prove mean value theorem as well as some other useful properties. Okay, before we get to the mean value theorem, let's see a couple more places where it does exist or it does work out nicely for us. For example, okay, Algebra 2, Algebra 1, Advanced Math Plus. We often want to define the zeros of a function. All the x's where the graph crosses the x-axis. All right, a lot of times that's difficult. All right, but Rolle's theorem can help us out a little bit. We got a couple of theorems here for you. All right, here's a special case of Rolle's theorem, Theorem 9.2. Not as important, it doesn't have a name on it. Okay, it says if f is continuous on the interval AB, differentiable on the interval AB, again, same hypothesis. All right, and f of x equals 0 has two solutions in AB. This makes it a special case. Okay, instead of f of a and f of b just having to be the same, they could be anywhere, but they're the same. This one says that has two solutions in AB. That means, hey, here's a solution 0, here's a solution at 0 here. So 1 and 3 both make that true. Okay? If that's the case where I got solutions, I got the graph crossing the x-axis in two places there, then what the special case of Rolle's theorem says that, hey, I know that I have a derivative equals 0 somewhere in between those 2 points. Okay? It's basically Rolle's theorem, except I've just shifted it down so that f of a and f of b are, in fact, on the x-axis. Guarantees I got at least one, okay? But I could have more. Okay, this one actually has 1, 2, 3 of them between those 2 points. All right, but the most important part of there is it has at least one solution. At least one place where the derivative is 0. All right, generalize that, we can actually do that for any number of solutions. Okay, if any integer n greater than 0, if f is continuous on an interval, differentiable on the same interval except open, and f of x equals 0 has n solutions, then the derivative of 0 has at least n minus 1 solutions. Okay, what that says here is that this, looks like it's a quartic polynomial. It has 1, 2, 3, 4 solutions, 4 places where it crosses the x-axis. This generalized theorem says, you know what? If I've got 4 solutions, then I know the derivative is going to be 0 for at least 3 places. Okay? At least 3. Could have more, but at least 3. So this one does have 1, 2, and 3. It could have more because when I come up here, this graph could do something like this. It gives me a few more, and this graph could do something like this. And I got a few more. This graph could do that. And it has a whole lot more. But it guarantees at least have one less solution to the derivative equaling 0 as the function does. All right? Well, how the heck is that going to help us out? All right, we can use those theorems to investigate the number of zeros a given function has. All right, let's look at this example right here. You'll have some problems to do like this. I want to prove that x cubed plus 4x plus 1 equals 0 has exactly one solution. All right, well, here's the graph of it. All right, surely does make sense. It seems reasonable that it has exactly one solution because we can see it crosses here at this one point. All right, but we only see the graph between -2 and 2. All right, how are we to know that this graph doesn't all of a sudden do something like this outside of our window and come down and hit it again? How do I know that's not true? Okay, because I don't see the whole graph. You can plug in your calculator and you can zoom out, but you never know. It could come over there like 1,000 somewhere and come back down, or 1,000,000. I'm not sure. Okay, I can only see so much on my graph. All right, but those theorems actually help us out. All right, so what we can do here is we can take the derivative of this thing. All right, if my function is x cubed plus 4x plus 1, well then its derivative is 3x squared plus 4. And now let's set this thing equal to 0. If I set this thing equal to 0, all right, we should notice some things. If I set this thing equal to 0 and try to solve this out, I'd subtract 4, divide by 3, and I get negative 4/3 is equal to x squared. All right, and what happens when I take the square root here? I take the square root, well then I'm taking the square root of a negative number, which gives me an imaginary solution. All right, so really, and we could have seen it way up here when we just did the derivative. We could have seen that, you know what? That derivative, 3x squared plus 4, no matter what I plug in the x squared, it's going to be positive. Multiply it by 3, it's still going to be positive. And add 4, it's still going to be positive. We know the derivative is actually always bigger than 0. Since it's always bigger than 0, this means there are no solutions to the derivative being equal to 0. All right, and since there are no solutions where the derivative is equal to 0, okay, if we look back at that previous theorem, it says that if there's n number of solutions to the original problem, then there's at least n minus 1 solutions to the derivative. Well, if there's 0, that means that there can only be one solution to the original. All right, and the reason why that's true, if you're not making sense to you yet, if this problem had 2 solutions, that theorem says that if this has 2 solutions, the derivative has to have at least 2 minus 1 or 1 solution. Well, since this one doesn't have 1 solution, I know this one does not have 2. Okay? If this one had 1 solution, doesn't necessarily mean this one doesn't have 2. It could still have 1, I'm not sure. Okay, the graph could do something like this. Well, actually, if it was just 1, it'd have to cross somewhere. It could actually have 2 and not cross again. But the fact that there's only 0, there's no solutions to the derivative problem, guarantee that there's only 1 solution to the original. Okay, since I can see 1, I can graph it and see 1. I know that is the only one that exists. All right, you could also think about it this way. If the derivative is bigger than 0, always, that means the graph is always going up. If the graph is always going up, then this graph never comes down anywhere. Okay, so it's going to cross to that one place, but it's never coming down. All right, so it's never, ever going to work. All right, and I believe that is all for this video. On the next video, we'll talk about the main event, which is the mean value theorem.